Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to introduce Nicolas Jacon from Besançon, who will speak about decomposition matrices and parametrisations of simple modules for Hecke algebras.
Thank you. Thank you for the invitation. So the aim of the talk will be to give way to parameterize the simple modules for Hecke algebra finite Lie group over the complex numbers, and to find explicitly this parametrization. Then we will focus in particular on type B, which will be the most important case in our context, and we will give the several natural parametrization for this Hecke algebra in type B, and we will try to give connection between these parametrizations. So I will first give the definitions, the background, and introduce the main object that we will study here, the decomposition matrix. So first, the notation. We set V is an indeterminate. And we will put A to be the ring of Laurent polynomial. So we will choose the square root of V for technical. And we consider A to be the ring of Laurent polynomial over V. And we will choose a map. So take W to be a finite Lie group. With a generating set S, which will be the set of simple reflection. Okay, then consider phi a map from S to Z, such that phi, so if S and T elements in S are conjugate, then phi of S is phi of T. And then, using this datum, we can associate the Hecke algebras associated to this Lie group. So H, A, this is the Hecke algebra. As W. So these are natural bases indexed by the element of the Lie group. So over here. And the multiplication is determined by the following rules. So TW prime is TW prime if we are in this situation, and otherwise the multiplication can be determined by the following identity, which is as follows. So W. Okay. So this is a deformation of the Lie group W, in the sense that if you consider a specialization from A to C, we send V to 1, then the Hecke algebra, the specialized Hecke algebra, will be isomorphic to the group algebra. So HC, the specialization of this Hecke algebra, is isomorphic to COW. So this is a deformation of the Lie group. And what we want to study here is the representation theory of this Hecke algebra in the general case. So the first case, which will be the easiest one, semi-simple case. We will first work with, we will extend the scaled of H to the field of fraction of A. So you get here the same Hecke algebra, except that we are over this field, and then we ask what is the set of simple modules for this Hecke algebra over K. And in this case, this algebra is in fact semi-simple. Split, semi-simple. And there is a theorem, which is the Tits deformation theorem. Which say that the simple module of the Hecke algebra over K are in bijection with the simple modules of the Hecke algebra, which is specialized when V is specialized to 1, so isomorphic with the simple modules of the Lie group. So this means that if you have, lambda is an indexing set for the simple modules of the Lie group, then you can say that the simple modules for Hk are labeled also by this set. So I will put E lambda, and I will keep here the record of K with lambda in lambda. Okay. So in this situation, the representation theory is well known. So for example, if W is the Lie group of type A, then this is known that so this is the symmetry group, and we know that the simple modules are indexed by the partition of n, so this implies that we can take lambda to be the partition of n. If W is type B, then lambda can be the set of couple of partition of n, so we say that this is by partition of n. So couple of partitions such that the sum of the rank of the partition is n. We maybe okay, so in this situation, in the semi-simple case, we have a parametrization of the set of simple modules for Hk. And now what we want to study is the case where the Lie group is not deformed by an indeterminate, but by complex numbers. So the situation here is we take a morphism from A to C, and we consider a specialized Hecke algebra. So this will be the same Hecke algebra, except that the deformation here is by the image of V, complex numbers. So you will have a specialized Hecke algebra. And you can ask the same question here. So is this possible to find the simple modules for Hc, at least have a labeling of the set of simple modules? And in this situation, in fact, this is not true in general, that you can take this indexed set for the set of simple modules. So so what we really want to do is to find this parametrization of simple modules for HC. And to do this, this is usual to work with this decomposition matrix, which is gives really an object to work with the modular representation theory. So HC in general is not semi-simple. And so I will define now the decomposition matrix, which will give a way to find these simple modules and to compare, in some sense, the this set that we don't really know with the set of simple modules here that we know. So decomposition matrix. The definition is as follows: you take, you start with simple modules of Hk that you know. So then you can show that these modules, E lambda k, can be realized over A, in fact. So there exists So this means that there exists a module over A such that if you extend these scalars to K, then you obtain the modules, the simple modules over K. Okay, so now you have something like a representant of these modules over HA, and now you can specialize this module to obtain a modules over HC. Okay, so you can define E lambda C to be the specialized module. And of course, in general, this module will not be irreducible, but we can compare these modules with the set of irreducible modules. So you take these modules, which is not irreducible, but we will have composition theory with the set of irreducible modules over HC. So M is a simple modules over HC. You take the multiplicity of the simple modules of HC on E lambda C. And you put all the number in the matrix, which is this the decomposition matrix of associated with this specialization. So we can show that this is well defined. And so you have an object which is which can control the modular representation theory, the representation theory of HC. So now the problem is, can you compute this matrix? And so I will come back later on this, but I will give, so here we have over the field of complex number, and in fact all these matrices are, not all these matrices, but in some cases these decomposition matrices are no. For the exceptional type, they have been computed by so Meinolf, Lux, and Müller. I think that's all, yeah. For type A, this is and type B. An algorithm has been given by Lascaux-Leclerc-Thibon. This were just a conjectural algorithm to compute, so this is just an algorithm, and proved by Ariki. So just an algorithm to compute the decomposition matrix. And in type B, Hecke as the Hecke's proof also is true for type B. So I will explain later what is this algorithm, and we can give the algorithm graph as given an algorithm also, and G also. And the only case where the decomposition matrix is not really known is type D. It's open in general. Okay. So now the natural problem, which is in connection with this problem of computing the decomposition matrix, is to parameterize the simple modules of the Hecke algebra over C. Of course, here you have only algorithm to compute the decomposition matrix, but this doesn't give really a natural way to have a parameterization for the simple modules. Okay, so this can be done by, so from now this is joint work with Meinolf, theory of basic set. And so the idea to parameterize this set of simple modules is quite simple. Look at this decomposition matrix. I will just give the definition here. So we keep the datum that we have. We have Hecke algebra. So this is associated to this map, phi. And you have a specialization. Okay. Then we say that that this admit the basic set, so with respect to theta and phi, if, so you have a specialization, so you can define the decomposition matrix. Okay. So the decomposition matrix here, the rows are indexed by the indexing set of the simple modules for Hk, so by lambda, one-to-one correspondence with the simple modules of Hk. And the columns here are indexed by the simple modules of Hc. And we say that we have a basic set if the decomposition matrix has the following form. For a good order on the rows of the theta. Okay, and now if you take only the first lines here, say that this is B, this is so a subset of lambda, then this subset is in one-to-one correspondence with the set of simple modules of Hc. So B is called the basic set. A basic set. And yes, if we just look at this decomposition matrix, then each of the simple modules are in correspondence with an element of B. So you really have a correspondence between this. So this set really gives a natural parameterization of the simplest modules for HC, this basic sets. Okay, so now we have this definition, and it is natural to ask if this basic set always exists in the context of Hecke algebra. And this is true. So this is a theorem by Meinhold and Rouquier. In the equal parametric case, then work of various authors can be used to show that this basic set exists for all choice of phi. So this is just for the equal parameter, that is when phi is always the same, is constant. So Deeper James. Ariklimatas. DXG, and can also add the people for the Euler. So says that for all W and for all choice of the map phi and theta, we have this existence of a basic set for the Hecke algebra. Okay, so this is theorem which gives now the existence for this basic set for all finite value group. And now what we want to do is to explicitly find this basic set. So yes, I have to say a little bit more on this. So if this basic set comes equipped with an order, pre-order in fact on the rows of the decomposition matrix. Okay, and the order that we have to choose here to have a basic set is the order induced by Lustig A-value. So the order. I will give example later. So Lustig gives a way, so this is used using the show elements of the Hecke algebra, gives a way to assign to each element of this set of lambda a certain value, which is called A value. And if we order the rows with respect to this A value, then we can show that there exists a basic set like this. So I don't give the definition because I will not choose really this. And I have also to say that this order, so this is an order on lambda, and this order really depends on the choice of phi. Okay. So depends on the choice of phi. So we'll give some example now for this existence of basic set. So first, study the case of Hecke algebra of type A. So in this case, And if we remember, when we want to choose this this map phi from S to Z, we have to take care to look at the conjugate of S. So we have to, in this situation, okay. If two elements are conjugate, then they must have the same image over this map. So in this situation, all the elements must have the same image. Phi is just constant, so Phi of S must be an element, so phi is just constant. And we will have two cases to consider. So first, so in fact, I will consider that A is different from 0, because this is the interesting case here. If A is, sorry, I have to. So I have considered W to be the while group of type A. I have choose phi, which is like this, and now I have to choose a specialization, and the specialization such that the Hecke algebra is non-semi-simple. So we choose this specialization. Okay. Why? Because if you if you choose another specialization, then the Hecke algebra HC will be semi-simple, and then the decomposition matrix will just be the identity, and you have nothing to parameterize because the parameterization is just given by lambda. So this is the only case which is interesting in this case, when we have this theta v is a primitive root of unity of order E. And if you want to compute the basic set which are associated with this, you have two cases to consider. If A is positive, then B is the set of irregular partition. So the set of irregular partition, that is, no part are repeated E or more times. And if A is negative, then it is easy to show that, in fact, the basic set is just the conjugation of the partition which appear here. So the conjugate of this partition are the ill-restricted partition. So this means that for all I, you have lambda I minus lambda I plus 1 is smaller than E. So this theorem says that if you are on type A, you have this decomposition matrix, and if you order according to the Lustig A value, which is in fact, which correspond to the dominance order here, you have this form for the decomposition matrix, and B is the irregular partition if A is positive. Then this is the ill-restricted partition if A is negative. So now type B, which will be the most interesting case. Okay. So the diagram of B is as follows. Okay, so you have put W, and now we want to have this map P. And here this is different from the type A case, because for the image of T you can choose something which is different from the image of SI, or the SI. So assume that phi of T is B, because this element is not conjugate to the other reflection. and phi of Si is A. And we will also assume that A is different from 0, because this case is quite different from the others. And we want to consider the same case here if we specialize to an element of C such that the Hecke algebra, the resultant Hecke algebra is semi-simple, then the simple modules, the set B is just set lambda, because d theta is just the identity. So we want really to consider the case where HC is non-semi-simple, and we are in the same situation here. So in fact, this is V up to the A. And this is the same situation. We can assume that theta of V to the A is a primitive root of unity of order E. Okay, so I will just recall the relation. So here the relation of the Hecke algebra. So here T is B. So these are the relation of the Hecke algebra. And I will just give an example of the computation of this basic set.
Small e is bigger than 1.
Sorry?
E is bigger than 1.
Yes. Yeah. Yes. Oh. So here is the example. Put A to be 1, B is 0, E is 2, and N is 2, so Hecke algebra of type B2, when V is specialized to -1. And then you can compute the decomposition matrix, which is given as follows. So the rows of the decomposition matrix are indexed by the set of bipartition. So these are the set of bipartition of 2. And the decomposition matrix is so now, if you want to compute the basic set, then you have to look at this Lustig A value, which give an order on lambda, the set of bipartition. So I put here this A value, which gives this order, and this is as follows. Okay. So if you want to have the basic set, you have to look at all these columns. The columns of the decomposition matrix, and look at the first coefficient, which is the smaller A value. So here this is this one, and here this is this one. So this means that the basic set are given by these two bipartition. Okay. Okay, now, due to this this choice of parameter, we will have another situation. If you now consider another map, say which is as follows. Then you still have a Hecke algebra. We still have an existent of the basis set. If you look at this, if you look at the same specialization, okay. But what you can see is now, if you take the so the relation of the Hecke algebra associated with this choice. And if you specialize V to a primitive root of unity of order E, then you have the same specialized Hecke algebra as the Hecke algebra before. This means that the decomposition map associated with this choice of phi is exactly the same as the one I gave before. Okay, so you have really the same decomposition map. You have the same algebra HC. So you have the same decomposition matrix. So I just have to okay, same decomposition matrix. But now, if you look at this theorem, which shows the existence of this basic set, the order induced by this Lustig value, the order of the row, really depends on the choice of phi. And phi is really different here. We have chosen this. This is not the same as the phi we have chosen just here. So the Lustig value will change. In this case, these are given as follows. And if you want to reorder the rows with respect to this A value, you do exactly the same thing. You look at each of the column and you take the smallest element which appear with non-zero coefficient. So in this column, this is this one, and in this column, this is this one. So the indexed set here is not the same. We have to, the basic set is given by this bipartition and this one, which is different from the bipartition that we had before. So. And what we really wanted to do at the beginning was to really find a parametrization of HC, and in this situation you can see that you have two natural parametrizations for the same algebra, HC. So you have really two parametrizations. And of course I have chosen this this phi here, but I can put 2, and then the order induced by the value will change, and maybe we will have other basic sets. Okay. So now what we want to do is to, so first, try to find all these basic sets in the case of type B. So we take W to be the value of type B, so computation of the basic set. And first, we'll assume that A is bigger than 0. In fact, it is possible to show that this is sufficient to understand this case to have all the basic sets, because we have isomorphism of algebra, which gives all the basic sets in the situation when A is negative, if we have this choice. So I will just give the theorem, which will not be very precise, but so we have chosen this map V. Then, so theta of V to the A is always a primitive root of unity of order 1. Of order E. Then, the associated basic set so this basic set will depends on the choice of phi, so I will put B and A in this basic set is the set of Uglev bipartitions associated to this choice of B of and A. Okay, so what is now the Uglev bipartition? There are some kind of bipartition which appears in a different context. I will say where, and which have not really easy definition, so I can't really give the definition here. But I will say how they appear. So if you want to compute the basic set, you have to look at this decomposition matrix. So you have to look at this decomposition matrix, and so as I said it before, the columns are indexed by the simple modules of HC. So we say that the simple modules of HC are in one-to-one correspondence with this, the columns of d theta. And there is a very deep theorem by Hecke saying that these columns are given by the canonical basis of a certain irreducible I-weight module for this quantum group. So this theorem is in fact the proof of the LLT conjecture, saying that you have this quantum group, so the affine special linear group, and there is a way to, you consider the category of irreducible highest weight module, and there is a canonical way to produce bases for these modules, which is given by this canonical basis defined by Kashiwara and Lustig. And Hecke's theorem says that these canonical bases specialized at 1 are exactly the columns of the decomposition matrix. So you really have a one-to-one correspondence between the columns of d theta, between the simple modules of HC, and the canonical basis for a certain module over the quantum group. And now,
There's also an order of the basis. Columns are the same.
yes.
It's not up to the order, the canonical order of the basis.
And the element of the basis? No, here we just have, we don't really know what is the correspondence between the simple modules. So so you have this canonical basis, and there is also a way to produce natural parametrization of this basis, which is given by the crystal basis theory. And gives this indexation of the canonical basis by this set of Ugloff bipartitions. So just what I wanted to say is that this set of bipartitions appear really on the side of the theory of quantum group. Okay, you have the decomposition matrix, one-to-one correspondence with the canonical basis, and on the canonical basis, you have a theory which says how you can produce an indexation of the canonical basis. This theory gives you that this is given by the Ugloff bipartition. And what we can show is that, in fact, the basic sets are really given by these Ugloff bipartitions. And if you look at what I said before, you can produce other... Now, if you look at another phi here, if you put phi of t to be b plus ae, then you have the same decomposition matrix, and you have another basic set. Okay. So here you have several basic sets, in fact, associated to this. And if you look at the side of quantum group, you really have the same phenomenon. There is several ways to index the same canonical basis by another set of bipartitions, which are called also the Ugloff bipartition. But associated okay, if you are on this side, you have several ways to index the same element, and the Ugloff bipartition in this case and in this case are really different. Okay. So of course, we'll have another way to index this element. Okay, so just to recall, if we have an Hecke algebra HC, not so simple, we have an associated decomposition matrix, and if we look at this different phi, we will have several basic sets, okay, which will be different in general. And what we show here is that each of these basic sets can be computed with respect to the way to index the canonical basis. Okay. So now, the problem is that we have shown that this, I said that the basic sets are given by this set of Ugloff bipartition, but it is very difficult in general to compute the Ugloff bipartition characterization. In fact, we only know recursive characterization of this type of partitions. So the aim at the beginning was to find a natural parametrization of the simple modules of HC, but at the end we only have a parametrization by a certain kind of bipartition which cannot really be computable. So this is the result is not so good here. So we want to find a way to compute explicitly this by partition, and this is in fact possible if you look at this case here. This is possible to have a non-recursive So we know that the Ugloff bipartition index are really given by this basic set. Have a nice non-recursive definition. So this is a result by Foda, Leclerc, Ocado, Thibon, and Welsh. So we are in one case, we know that this basic set, this Ugloff bipartition, have a nice parametrization. Okay. We can also show the following thing, that the basic set indexed by minus b and a is only easily computable using the basic set indexed by b and a. Okay. And so you can see that you have a bijection in this and this. So now assume that we have this. So we are in this situation, so we have this basic set, BA, and as I said before, we have an easy non-recursive characterization of this bipartition, and we know that this set is in one correspondence with this set. And if we now look at another phi, we know that this basic set is in fact a basic set for the same decomposition matrix as the choice of parameter. So this is also, these two basic sets are in bijection. And you can also choose to okay. So you have bijection also with take the opposite of the first parameter. Okay. Now, if you look at the specialization at the phi associated to minus b or a, we can do exactly the same thing as I said it before here. You can just add a multiple of e, and you also have something which is in bijection with this basic set because you index the same decomposition matrix. And of course, this is in bijection here. Okay, now consider the extended affine symmetric group of rank 2. So indexed by then what you can see is that this group, extended affine, acts on the set. Well, this is not. On the basic set, just by permuting here by sigma, the action of sigma on this element here given here, and the action of y0 is by adding just and you have the same here. Okay, so the problem was to find all these basic sets. And as I said before, we know one good characterization of the basic set. This is this case. So if you know now the orbit of this action, then you know, if you know really how this y0 and sigma act on the basic set, then you have a characterization of all the basic sets. And in fact, this is possible to do this. First, the action of sigma is easy. This is just permuting lambda 0 and lambda 1 here. So and if you know how y0 acts on the basic set, then you know all the basic set, and this is possible to compute this action. There is an explicit algorithm which is given using really the notion of Ugloff bipartition, and using really this the fact that this bipartition index the canonical basis of the irreducible Elliott-Sweet modules. So this is so as you know now really the action, and as you know all, as you know the characterization of this basic set, then you can obtain all the basic set for all the choice of parameters here. And okay, I finish now.
Okay, thank you very much. Are there questions, remarks?
Répétit by phi de positive characteristic.
So all these the existence of basic set can be proved also, but using Lustig conjecture. So we have to assume certain Lustig conjecture. And in this case, this is possible to show that all these basic sets are exactly the same at the characteristic 0. But we still have to assume Lustig conjectures, yes, which are, for example, known to be true in equal parameter case, but not in all cases.
Does such thing are true for affine Hecke algebra?
I don't really know. Yeah. So there are connections with affine Hecke algebra of type A, but we don't really know.
Questions? Or let's thank the speaker again.